Hello, welcome to S Chemistry. I am your instructor Dr. Suhas Gauli, and today I will be teaching BSc 5th semester Physical Chemistry course on colligative properties of dilute solutions. So here is the outline. In this class I am going to cover osmosis followed by osmotic pressure followed by Berkeley and Hartley method. So let us start with osmosis. So what is meant by osmosis? As the right hand side you can see the figure illustrate the process of osmosis. As you can see, one beaker is there, and in beaker you have two different compartment, and that compartment is divided by one simple semi permeable membrane. So this membrane is such a way that the only solvent molecule can pass. So the solvent molecule can pass through the membrane from either side of the semi-permeable membrane. So it can go from right to left and left to right. So only solvent molecule can go. So there is a net flow of solvent from dilute solution to the concentrated solution. So here dilute solution means number of particle is less. So as you can see, solid molecules has only 3 particle over here, and in this compartment you have 5 particles. So here more concentrated solid concentration is there, and here it's diluted. So in that way it's a concentrated and dilute solution. So let us see what is in by osmosis. So the osmos is a Greek word. So osmos means to push beyond their membrane. So let us consider a pure solvent and solution prepared by a membrane which permits the passage to solvent molecules but not to the solid molecules. So only the solvent will diffuse through the membrane into the solution. So diffusion happens always in both ways. So it can go from higher to lower and lower to higher. That is only applicable for the solvent. So you can say that is for the osmosis. So let us see what is meant by membrane. So a membrane which is permeable to solvent and not to the solute. So you have this water molecule here, that is the solvent molecule, blue color is the solvent molecule. So only these blue dots can move from here to here and here to here, left to right and right to left, and not this pink one, that is solid molecules. So this kind of membrane we call it semi permeable membrane. So semi permeable means only half of the portion can pass through that membrane. So that's why it's a semi permeable membrane. So that is the meaning of that word. So let us see what are the examples of the osmosis. So as you can see in right hand side, the resins, this is a resins we generally eat in the morning time. So if you resin in the dried form, that is shrinked one, so inside you have less amount of water, so that is dried one. If you keep it these resins into the water or solution, resins will start to swell. So you will be having bigger size compared to this resins, so dried one. So this indicates that your solvent, that is here water, is passed through this resins semi permeable membrane, and that's why the water go inside the resins and it starts swelling. So this process is a natural process is occurring. So this the illustration of the process of osmosis. So this is the best example of osmosis. So here the water molecule can pass through the membrane of resins from outer side to inner side of the semi permeable membrane. So here semi permeable resins, whole resin act as a semi permeable membrane. So only water can pass through that. So what is the moment in osmosis process in this case? So solvent molecule through a semi-permeable membrane is taking place in both direction. So in any kind of osmosis process, your solvent molecule can pass in both direction. That is the first moment. And second moment, so diffusion of the solvent Solvent where to where will go generally. So diffusion of from solvent to solution or from dilute to concentrated solution, so is more rapid. So the net flow of solvent is the from low to high concentration. So as you can see, outside is a low concentration of the solute, that means there is no resins, and inside the high concentration of the resins. So your solvent molecule will always flow, solvent will always diffuse to the low to higher concentration. So inside concentration of the sugar or a resin molecule is more, so that's why your solvent will go in that fashion. So these are the two types of movement occurs in the osmosis process. So what is the example? So many natural membranes are the semi-permeable membrane. So you can think of any natural membranes generally. So this resins is the best example in that, among that. So now we will see the osmotic pressure. So what is meant by osmotic pressure? So as you can see in right hand side, the figure illustrate the meaning of osmotic pressure. So far we have seen osmotic or osmosis process. So in same osmosis process, you are applying the external pressure to the particular chamber. In so this we are applying such a pressure that so on the solution to stop the osmosis is equal to the osmotic pressure. So whatever the solvent flowing from lower to higher concentration is going on, so that will stop. So you have to apply external pressure up to that point, so your whole the osmosis pressure should get stopped. So here you can see in this figure you have these two chamber, one is water, simple water, and another is simple solution. So solute concentration here is almost negligible, so here low and here high. So generally lower to higher concentration solvent is moving, like water is moving, but if you apply particular pressure, so your solvent will not grow. Here this level will not increase, so that's why you will get here some flow. So this flow indicator, so here this capillary action will show how much solvent is moving from here to here. So you have to apply pressure in a such a way that your flow of this line should not get flow. So that is called osmotic pressure. So if you see in terms of a definition, so the hydrostatic pressure builds upon the solution which just stop the osmosis of pure solvent into the solution through a semi-permeable membrane. So it's called the osmotic pressure. So you have this hydrostatic pressure. There can be two types of pressure. The one is hydrostatic and another is external pressure, as you can see in this figure. So the hydrostatic pressure builds upon the solution. So what are the pressure you are applying to the solution? So we have to apply pressure in a such a way that so which just stop the osmosis of pure solvent into the solution through this semi-permeable membrane. So it is called the osmotic pressure. So here again membrane means the membrane which is permeable to the only solvent molecule and not to the solid molecule. We call it a semi-permeable membrane. And what are the types of the pressures? So first type is hydrostatic pressure and another type of pressure is external pressure. So these two examples we have. So this is the example of external pressure which is given to the outside the solution. So what is the moment in this osmosis process? So in the osmotic pressure, so there is no moment. So everything is at still position. So what are the to stop the osmosis of the pure solvent, we apply only that much pressure. So net moment of this in the osmosis process is zero. So there is net is zero. So what are the example of osmotic pressure? So many natural membranes are semi-permeable. So best example is process of pickling. So as we day to day life we eat pickles. So that is the best example of osmotic pressure. So how this osmotic pressure works in pickling? As you can see in right hand side, so these are the types of vegetable pickles. This is I think this is cauliflower pickle, this is carrot pickle, and this is cucumber thing lady cucumber pickle, and this is mango pickle. So how this osmotic pressure works? So the osmotic pressure involved in the pickling is critical to understanding like how the process works. So osmotic pressure is main key role or critical role in pickling. So how the process works? So pickling of vegetables. So this is the best example of osmotic pressure. So how process works? So first we have to prepare the brine solution. In brine solution, we have generally the pickling process start by preparing a brine solution, which is typically consist of water, vinegar, salt, and often sugar and spices. So we generally put in pickle, we add like some oil, that vinegar or salt, or often sugar and spices. So the solution high has a high concentration of solute. So outside you have high concentration of solute. So that is mean you have salt or sugar concentration, outside is more. So we call it that is the brine solution, which is in the liquid form of the like over liquid form of the pickle. So in this brine solution we generally immerse the vegetables. So what are the vegetables? We generally just immerse. So which kind of vegetables? So vegetables such as cucumber, carrot, or pepper are placed in a jar and then immersed into the brine solution. The high concentration of solid in the brine creates a high osmotic pressure. So whatever the outside liquid is there, that is brine, so it creates the osmotic pressure. So we just preserve in that case vegetables. So third point process is the osmotic, how osmosis occurs. So in this occur, the vegetable cells have a lower concentration of solute compared to the brine. So vegetable also have some osmotic pressure inside. It also has some lower concentration of the solid, and outside is a higher. So we know that, so from lower to higher concentration your solvent flow will go. So according to the principle of osmosis, water inside of the vegetable cells move out into the brine solution. So whatever the inside water is there, like in cucumber or in carrot or in cauliflower, so whatever the water, it will go into the solution phase or in the brine phase. So that's how your cell membrane breaks, and this brine solution through the cell membrane is equalize the solute concentration on both side of the membrane. So that's how it equalize the solute concentration on both side. So that's how the osmosis occurs. The fourth process is effect, how this osmotic pressure effects on vegetables. So as the water leaves the vegetable cells, the cells shrinks and becomes less rigid or turgid. So the loss of water helps to preserve the vegetables by reducing their water content. So as the water content is lesser in the vegetables, so that's why the pickles generally get shrink. So which inhibits the growth of spoilage microorganisms. So there will be no movement of microorganism, or there will not be grow any growth of microorganism. So the salt and vinegar also contribute to preserve by creating an environment that is hostile to bacteria. So inside there will be no bacteria, and that's why there will be no spoilage of vegetables. So that's why pickle has more shelf life compared to the normal vegetables. So it also affects the flavor and the texture of the vegetables. So during this pickling process, the vegetable not only lose water but also absorb some of the brine flavors and acids. So whatever we are adding some solvent, that is brine or acid or sugar, it will absorb. So it will also change the flavor of inside vegetables. So this change and the texture of the vegetables, giving them a characteristic flavor of pickle foods. So that's why we have pickling of vegetable have different flavor and food texture. So in summarize way, you can see in pickling, osmotic pressure drives the movement of water from inside the vegetable cells into the surrounding brine solution, and this process helps to preserve the vegetables and give them a desired taste and texture. So this is the day to day life we have best example of osmotic pressure. Now let us see the methods, like how to measure the osmotic pressure. So one apparatus is there, that is Berkeley and Hartley method. So Berkeley and Hartley is a two name of different scientists, and they invented this apparatus. So we will see this how this method works. So the hydrostatic pressure builds upon the solution, which just stop the osmosis of pure solvent into the solution through a semi-permeable membrane is called the osmotic pressure. So this is the just example or definition of the osmotic pressure as we have seen in the last slides. I have given here one more time. So here the best example is hydrostatic pressure, where you have this water inside beaker, you have water. So inside this is the your semi-permeable membrane, and inside you have sugar solution. So from outside water will not go. So initially it was this level, but as the inside concentration of sugar is more, the solute is more, so outside water will go inside. So you will hydrostatic pressure will increase, or it will increase the maximum up to this level. So now you will see the example of osmometer. So as right hand side in figure you can see the Berkeley and Hartley osmometer. So you have solution, solvent, again solution, and you have above pressure, and here you have to measure the pressure gauge. So in this way they have developed this osmometer. So you have this green color, you have this proclaim tube, that is a semi-permeable membrane which is made up of carbon and iron salts. So here you have outlet, here meniscus level is here, and here is the solvent reservoir, and inside you have solvent, and here you have solution. So this hole is made up of metallic jacket, and this we have a capillary tube of which is made up of glass. So now let us see how this method works, or osmometer, which is invented by Berkeley and Hartley in 1904 and 1909. So they employ the technique of applying external pressure on the solution just enough to prevent the osmosis. So whatever the solvent molecule is there, it should not get diffused into the solution. So that much only pressure they are going to apply, and that pressure they are going to measure over here. That is your osmotic pressure. So this is the apparatus. So apparatus contains proclaim tube with a copper ferrocyanide membrane, which is deposited in its wall, is enclosed in the metallic. So, and the tube is fitted with a reservoir, as you can see, and right hand side you have this solvent reservoir that is in water at one end, and the capillary tube at the this end should be open at the other end, and here you are applying the mechanical pressure uh, that can be applied on the solution. We are applying pressure on solution with a piston connected to the pressure gauge. So here on pressure gauge you can see the how much pressure we are applying, that is mechanical pressure. So what is the procedure to measure this osmotic pressure? So first, the inner proclaim tube is filled with a pure solvent, and jacket with the solution whose osmotic pressure is to be determined. So we have to water solution which is your analytes, we have to put over here just to measure the osmotic pressure. So proclaim tube is a tube which is used as a semi-permeable membrane. So the level of solvent meniscus in the capillary tube will tend to move down as the solvent flow into the solution. So this solvent, if you are going to the solution phase, so this level will decrease. So that's how we can observe So we have to put this pressure so that this level and this level has to get balance. So the pressure is then applied through the piston so that the meniscus becomes stationary. So this meniscus, what are the is, this has to be get stationary. Up to that level you have to put the pressure or mechanical pressure. So it indicates that the osmosis has been stopped. If this meniscus level has stopped, we can consider as the osmosis process also stopped. And now the pressure record by the pressure gauge is gives the osmotic pressure of the solution. So that's how we measure the osmotic pressure. So here we come to end of this lecture. So these are the references for the images, and for the content these are the references for the books. So thank you for kind listening. See you in next lecture. Till then, happy learning.